Uh, yeah, so we start today's session. So unfortunately, Vijay is not able to give the talk that he was supposed to give, and instead Michael Hatridge will continue with the lectures, and he will give the talk that Vijay was supposed to give. Maybe that's more efficient. Okay.
Okay. Good morning. It's me again. Vijay sends his apologies. He's not well this morning. So this is going to be the second talk in our series. This is Vijay's talk. You'll notice there might be slight pauses as I try to figure out what slide I'm talking about right now. But roughly speaking, we're going to pick up where we left off yesterday. We've talked about what parametric amplifiers are, what quantum measurement is, and today we're going to work through how to use this particular phase-sensitive amplifier that was used first at Yale and then Berkeley to good effect, and now in Vijay's new lab. And we're going to kind of take a little bit of a historical approach. So we'll talk about bifurcation, then leading into this phase-sensitive amplifier, some single-shot measurements, and then the more recent stuff that Vijay has done. And just like last time, I would encourage you, don't push whatever button that was, to stop me with any questions as we go along. Okay, so to begin now, firmly in the superconducting realm, here once again is our Josephson junction. This is the workhorse of every superconducting device we build. It's again two superconductors here, a lower one and an upper one. This is actually more what they look like. They're built in this sort of overlapping geometry. And again, the barrier is this thin aluminum oxide insulator here. The two superconductors are typically aluminum. This is the circuit symbol we use for it, this kind of X crossing a line. It has the first Josephson relationship here says it's a nonlinear object. The current that flows across it in response to the phase difference in the superconducting order parameter of these two electrodes is sinusoidal with some maximum current I naught. And the second Josephson relation here says that the junction voltage is going to be proportional to this reduced flux quantum here, h bar over 2e, times the rate of change of the phase difference across the junction. And so I think one sort of question about these junctions, even in the superconducting community, is sort of what regime we're going to operate them in. Historically, people would tend to take these junctions, they would shunt them with a resistor and a capacitor, and then they would bias them to the critical current. They would switch into what's called the voltage state, and they would have very different behavior. Here, however, we're going to always keep them in the superconducting state. So even though we have the same equations of motion, the behavior is going to be a little different. So we're going to always let there be no static current across this junction at or near the critical current. And in this case, we can think of this circuit symbol as kind of a nonlinear inductance. So we can define some LJ, some Josephson inductance, which is again given by this reduced flux quantum phi naught over I naught. And now you see it's a nonlinear inductance because there's this cos phi in the denominator. And basically you can take these two equations, say that an inductor should have V equals L di dt, and work this out here. And what you see is that if the phase difference is small, then this cos delta goes to 1, and this just becomes a linear inductor. But as you drive the thing in a microwave way harder and harder and harder, basically you'll see that the inductance changes. And this is a very classical description. We'll get back to A's and A daggers eventually, but this is the secret to everything that we build, this nonlinear inductance right here. We can't always fabricate them exactly the size we would like, so the trick we commonly use here is to take two junctions in parallel in a superconducting loop. Now we have the requirement of flux quantization around this loop. And what that does basically, you can kind of think that at zero flux, these two junctions add like capacitors to be one junction twice as big. But by modulating the flux through the loop, we essentially get a junction whose Josephson energy and Josephson inductance we can tune as a function of flux. So this is just a nice in situ way to tune this inductance if you don't fab it to exactly the value that you'd like, or if you'd like to change it as a function of time. So taking all this together, we have a flux-tunable, nonlinear inductor, and that's going to be the basis for basically everything else we talk about today. Okay. Oops. So now, here is my nonlinear inductor. It has some self-capacitance, so there's the capacitance of the junction. I'll often connect it either to a microwave port, or think about it in some lossy resonator, and I'm going to, right here, I'm going to assume that I'm driving a current. So kind of a microwave port we're replacing by the resistance of that port and some current drive. And here's the equation for the current of time through this circuit. It's basically Kirchhoff's law. You have the resistor, you have the capacitor, and you have the Josephson junction itself. And then you see here that this is a harmonic oscillator. I can work out that if I drive this system, I basically have something like a mass, like a drag term here. And then I have, now here VJ's added one extra piece. This is the junction itself. And this would be static current that is shunting this junction. And this would be a more typical sort of historical thing to do, to apply some current here, for instance, that would take this potential, this cosinusoidal potential here, and sort of tilt it downwards. We're not going to consider that today. That's maybe something that's more historical. Today we're going to basically just only apply microwave signals. The sort of flux particle of this junction is going to sit in the bottom of the well, and it's going to oscillate around this as we drive it. Okay? The junction itself then and the capacitor form a resonator. This resonator is nonlinear. And so what you see here is that here's the full potential landscape of this object. And if we sort of look at low energies, it looks parabolic. It looks like a harmonic oscillator. As we drive it harder and harder, we see definitely that we're in a different shaped well. And if you look over here now, the natural frequency of this oscillator is not constant. It's a function of the drive. So at weak drive, so for very small oscillation amplitude, it has the normal plasma frequency 1 over root LC I would expect for a harmonic oscillator. But as I drive it harder, it has a definite tendency towards lower frequency. So this oscillator has the interesting feature that if you drive it, let's say, above resonant frequency, it's always off resonant. If you drive it below resonant frequency and now you increase the amplitude of that drive, you can find yourself back in resonance with the system again. And again, to solve these dynamics, we have some microwave current drive. The system will respond harmonically. That is, this flux particle in the well will move harmonically. It'll have some amplitude and some phase it'll respond with. And again, we calculate the voltage by figuring out the derivative of this phase as a function of time. Okay, and classically, if we, as you'll see sort of more explicitly in a minute, this physics is often associated with this thing called the Duffing oscillator. This Duffing oscillator is a nonlinear resonator which has a particular decreasing frequency as you increase the drive. And what we have here now is, here's us driving at different frequencies. So here's the frequency of the drive normalized by the plasma frequency. So here's the linear resonant frequency. And these different colors represent different amplitudes of drive. So you see you drive it very weakly, you get the normal sort of linear response that you like in terms of the oscillations in the junction as a function of the drive frequency. But as you drive it harder and harder and harder, you see that the resonant frequency, the peak of this guy, the peak response moves down and down and down. The curve kind of shifts to the left, kind of starts to look like a shark fin. And eventually it kind of goes vertical, like at this green line here. And past that, it bends back on itself. And that means that basically you have two stable oscillating amplitudes for a given drive frequency. And these are all drive frequencies below the resonant frequency. So this situation here, which occurs below this critical detuning, is a dynamical bistability. And if we take the cosinusoidal dependence of the junction, which in these dynamics becomes a sinusoid, and we just expand it out to the first two terms, we get this classical guy here. There may be different, flux quanta in there compared to your usual treatment of the Duffing oscillator, but this is just exactly the Duffing oscillator dynamic. So this system is a bifurcating system, as was asked yesterday. And so what people did in Michel Deveray's lab was to really look at this thing and to use it, as I'll show you, as a qubit detector. But basically, the first test that they did was take this system here. So here's my bifurcating system. We put some following amplifiers so that we can digitize everything at room temperature. We have a network analyzer, and what this is basically doing is sending a voltage or current wave into the system and then measuring what reflects off the system. And so what you see here, here's the phase response of the system as a function of frequency. You get this typical phase response curve for a linear resonator when you drive weakly, with a Q given by omega RC in the usual way for a parallel LCR resonator. And here now is the phase response graph. So every, let's see, horizontal line here represents a different sweep of the vector network analyzer, where every time I've increased the power. So I sweep, increase the power, sweep, 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 sweep. There's plus 90 degrees. Red is minus 90 degrees, yellow is resonance, and what you see here again is this resonance frequency. As I increase it, it bends backwards, and then eventually goes into a scenario where it starts to bifurcate. And in that scenario where I'm driving very strongly, you can see here that the phase response kind of has a very sharp step in it as it's basically stepping from one solution to another. And in this particular case, they also had the ability to measure the DC voltage across the junction. So that's this purple line here. And what they're showing is in this scenario where this system is bifurcating, there is no DC voltage. So this is really a clean microwave dynamical bifurcation, not something funkier. And the good reference here is Vijay's thesis from Yale. Okay, now to prove that it bifurcates, we want to look for some kind of hysteresis in the system response. So what we have here is the phase of the microwave response. Here's the drive strength, so here's increasing drive. And what you basically can see is that if I start at low power and I drive upwards in power, I get one response, I switch to a different solution, keep going. Now when I come back, I stay on this upper solution for a while and then drop back. So this hysteresis here is basically exploring the bifurcation wedge, is exploring the upper and the lower solutions, and as a function of the drive frequency and other system parameters, you know, this can have different sizes and different dependencies on current difference. Now, the other thing we can do is sit right here, so as to bias our system up, and then sit right at this 50-50 switching point, right at the place where your system can dynamically bifurcate. If we make a histogram, so here's counts here, and here's different phase bins, you can see that the system will dynamically bifurcate basically 50% of the time into this one with this average phase value, 50% of the time into the high state with this other average phase value. If you just sort of now want to average longer to know this phase better, what you can do is this kind of ramp and hold. So what you do basically is you turn it up very briefly to very near the switching point, this 50-50 switching point. Now you drop it back down so that if you're in the upper solution, you'll stay in the upper solution. If you're in the lower solution, you'll stay in the lower solution. And then you can basically average as long as you want and get a much cleaner knowledge of this phase here and a much tighter histogram. And this right here is one of the key features that we're going to use this bifurcating amplifier as. We're going to use it sort of two-step process here. Step one is to let it dynamically bifurcate and capture some piece of information, basically the critical current of the junction, and then to let it hold and stay in that state as long as we want. And the reason this ramp and hold scheme is so nice is because even if you have no parametric amplifier, even if you have kind of a very noisy following amplifier, you can always just integrate long enough to figure out which of these two states you're in and get a very nice readout. So this historically was the first use. Yeah.
The microwave signal, is it?
Yeah, that's right.
That's what you're...
yeah, it's more explicitly shown here. So the device is not complete without a circulator. So basically what you're going to do is impinge some microwave drive here. It has some amplitude and phase. It's going to interact with this guy. Because it's a reflection resonator, all the power that enters comes back. So the amplitude contains no signal. The amplitude is always 1. All the power that enters comes back. But now this outgoing signal is going to have a phase, and the value of that phase is going to basically tell you whether or not the system switched to the high state or stayed in the low state. We always are driving the system up from 0, so it's always starting in the low state. So the output here, the reason we're always plotting phase here on all these graphs is because in this reflection, what's called microwave reflectometry, the signal's all encoded in the phase.
But you measure both the amplitude and the phase of the reflected.
The VNA measures both.
Okay.
But we throw the amplitude away because we probably digitized it in the real experiment, but it doesn't encode information. Because it's this fact of a reflection resonator, if you don't have internal losses, all the power you put in has to come back. So no matter if you sort of have off resonance drive, on resonance drive, if you look at the amplitude versus frequency response of a reflection-driven resonator, the amplitude is always 1, even though the phase changes. So if you have internal losses, you might get some kind of dip. And if you have some shift here, you might have some small signal in phase as you move, for instance, the resonator frequency around. But in general, in this reflection setup, all the information about where the resonant frequency is and what the state of the resonator is encoded in the phase. This is very different than transmission. Maybe you're more used to transmission. In transmission, if you're off resonance, light doesn't go through the system. In reflection, if you're off resonance, the light bounces off. If you're on resonance, it dwells in the resonator for a while, picks up a phase difference, and then comes out. But in both cases, it comes out. So that's why this amplitude here is just a flat 1. That answer the question? Okay.
Yeah, I missed some part of your talk, but I'm wondering, so why the reflection amplitude in the absence of absorption has to be 1? Because I thought, naively, energy conservation will tell you summation of reflection transmission is sum up to be some constant.
Right, but you see here, there is no transmission. You see,
okay.
we have a circulator. So yeah, this is going to come up a lot in the next 2 days. So let's look at it right here. These experiments that VJ and I do tend to operate in reflection. So there is one port here that you're impinging on. And so conservation of energy says that the output energy has to be the same as the input energy, unless there's internal losses in the resonator. So that's why. Okay. And the key thing to realize here is that, this is the readout, right? Its amplitude is important and its phase is important. Its amplitude has this funny profile here that determines this sort of moving to 50-50 latching and then moving away. So the amplitude matters for that. The frequency matters because you have to, again, move to a low enough frequency below resonance to find a place where the amplifier bifurcates. And then the phase now is going to be the free variable that tells us information about what's going on inside the amplifier, about basically whether or not the amplifier latched to the high state or stayed in the low state. And so what you can think of this system as, it's an amplifier in that it takes a small change in critical current here. So if I was to apply some all drive to this junction to change the critical current, if I was applied a flux to the squid or bias current to the device, changing the critical current would change the latching probabilities, because I'd basically be moving closer or further away from the bifurcation point depending on whether I move the resonator up or down in frequency. So it's an amplifier, not in the sense of increasing the voltage. Again, the voltage is a constant here. We don't even pay attention to it. But what it can do is to take a very small change in critical current and make a very big swing in the voltage that comes out. And so now here, if I look at different drive amplitudes here in different phases, you see here, for instance, for a small change in critical current, I can have this kind of discrimination wedge. If I sit right here in the middle, where the blue case has very low switching probability and the red case has very high probability, then I can get a very large and easily discriminated signal. And if my amplifier that follows this, if my microwave readout chain is noisy, because of the latching part, I just sit there and I integrate for as long as I need to get my signal. The other key features here is that no power is dissipated on chip, and that I never switch the current, I never exceed the critical current of this junction. I never switch the current to the voltage state. At the time this amplifier was being developed, this was a common thing to do, with have some squid who you would switch to the voltage state, get a large, readily read out voltage signal. The problem here was dynamically at dilution refrigerator temperatures, it would take something like a millisecond for the junction to fall back to the superconducting state. So there was a really long reset time. This one had a very fast reset time, some few hundred nanoseconds, and so you could read out something like 1,000 times faster. So historically, that's what this guy was developed for, and they were happy because of the fact that there was no on-chip dissipation of energy here, because on the next slide, I'm going to show you the next step now, how I'm going to change this critical current, the thing that provides the signal to my amplifier, is going to be this charge qubit here. So this thing right here, we've got an island in the middle, these two small junctions. Basically, this is a qubit where the state of the qubit is the charging state of this island right here in the middle, which I'm going to manipulate with this microwave and DC voltage from the side. So what you can think of it is doing is, here's this object, it's kind of an asymmetric squid-looking object. When I change the state of the qubit, it changes the effective critical current of these three junctions acting together. Again, changing the critical current changes their latching probability, and therefore when I do that, I'll see, one phase, let's say 0 if the qubit's in the ground state, and 90 degrees if the qubit's in the excited state, and that's how I'm going to read out my qubit. I'm going to read out my qubit by first putting it in some superposition state, then driving the circuit with a microwave drive tone. When it comes in, forces the bifurcation part, the right-hand side here, to latch or not latch, encodes that in a phase of the output, and by sitting here and monitoring the phase, I figure out the state of the qubit. Yeah?
Can I ask you to go over the mechanical analogy of the Josephson bifurcating amplifier, this switching behavior, like in terms of the sort of part in a sinusoidal potential? Yeah,
so it's like a pendulum. Yeah. If I drive the pendulum weakly, it stays in one state. If I drive it harder, it's suddenly amplitude. If I drive the system weakly, it just looks like a harmonic oscillator. If I drive it strongly, the harmonic oscillator frequency slows down.
So it suddenly jumps to a
So
larger
if my drive is
amplitude,
low
but-
enough in frequency and high enough in amplitude, if I drive it for 1 or 2 or some number of periods, it will decide with 50-50 probability if I've biased it correctly. This is a choice of bias. That at the end of that response time, it will either stay in a small oscillation state or it will have a big oscillation state. And it will stay, there's a hysteresis in the system, right? If I go back to the hysteresis loop here. So if I come up to right here before it switches, you know, so there's some bias point right here where I have a 50-50 switching point for a certain amount of time. So it'll make a decision, it'll go high or low, it'll stay here or here. And if I now turn the current back down, as long as I don't go below this value here, it'll stay latched into that state. So mechanically, it's a pendulum again. It's going to go low or high at the end of some number of cycles of a carefully chosen drive, frequency and amplitude.
And this is perfectly classical.
That's all classical. It's a quantum object doing it, but the dynamics are all classical. Okay.
So, but now, if you want like a superposition, then it just switches between these two states, is it? Or it's not really.
Think of this as like, yeah, a von Neumann measurement. If your psi initial is some alpha g plus beta e, then your pointer system is going to be the outgoing phase. And you will measure this high amplitude phase with some probability. The probability of getting that phase is going to be, you know, g psi initial mod squared. And then phi low is going to be this one. So this will be alpha squared. This will be beta squared. So this is exactly like the sort of pointer variable in a sort of textbook version of a von Neumann measurement. And all of the projective action is basically carried out by this microwave drive here. So this microwave drive is going to query the system. It's going to ask, what dynamical state are you in? And of course, if you start in some superposition state, the output of this thing will be quantum in that it will also be a superposition of high and low. But then as that information reaches you, the receiver, you very quickly project it onto this one or that one. You don't look happy with the answer. So, yeah.
When you do the measurement, you're saying like with probability alpha mod square, you'll get both these outputs with these probabilities.
That's right. So if I do this a bunch of times, and I do again a histogram, I'm going to get, here's my phi low, here's my phi high. I will get some histogram like this, and if hopefully I do it right, then there will be some noise in the system, but I'll get a Gaussian distribution centered on phi low, a Gaussian distribution centered on phi high, by measuring the areas under these curves, back out alpha squared and beta squared, the probability of my initial superposed state.
But this thing is it? I mean, is this still captured by that equation, the Duffing equation? That
no, right.
That's not.
The Duffing equation is just saying that the amplifier has this bifurcation here. To sort of now go into the quantum regime, I have to, of course, do. I mean, the correct thing to do would be like the stochastic master equation. What they actually did in this experiment is just to know kind of that the right thing was happening. There are complications. So let me go forward a little bit. So there are complications. There are backactions and stuff like this that are not captured in this sort of classical idea that just sort of there's something that moves your critical current and forces you to latch or not latch. Sorry to go high or low. But yeah, if you sort of give me this classical picture here that there's something classical on the right, which is my pointer state, and on the left here is something quantum, we can at least sort of understand roughly what's going on. And I'll talk a little bit about the complications in a second. Okay, and so what they do experimentally here is we excite or not the qubit. Apparently this particular one had like a 20 gigahertz excitation frequency. Again, we put in our drive pulse and we look at the phase, which he's drawn here, red response. of the output pulse. So here's the data. So this is him doing a Rabi sequence. So he's varying the time of this Rabi drive. So that's driving the qubit from the ground state to the excited state and back with a certain Rabi rate as a function of time. That's this oscillating period. And at the end of every one of these experiments, then he is measuring. So here's his measure. And again, it's ramp up, latch, and hold. And every point here then represents, I don't know, some 10,000 or 100,000 averages. And when you do this, you see nicely here's the Rabi rate of the qubit, and this relaxation right here is T1. Okay, so this is the energy relaxation of the qubit. So, you know, quantum complication number one is that the qubit doesn't necessarily hold still. If it has a short time, and this takes some reasonable amount of time here, of course the qubit is going to undergo dynamics even while you're trying to latch it. So the effective critical current of the circuit, instead of being a rock-solid variable, is some stochastic variable that's changing in some way versus time. So that's problem number one, is that the qubit, in this case, I don't know, it looks like 300 nanoseconds or something like this. It's a pretty short-lived qubit. This was 2002-ish. But the thing that people are very excited about back in this time was that instead of having a few percent qubit readout, you see that the difference here is 80% switching probability here and maybe 20% switching probability here. So that's something like 60 to 70% single shot fidelity. And this was a very big deal at the time. And the other key thing here was that it was single shot fidelity, and it was very rapid in that they could turn the amplifier off for a few hundred nanoseconds and then reinitialize and be ready to go again. So this was a very fast, very high fidelity readout. Okay. So you see Heekin says we can measure signal to noise of 100 to 1 in a few minutes. So it's very fast. Now, I guess, yeah. So the question to ask here is, if this bifurcation amplifier is so good, why is it not 100%? So here, again, here's the switching curve. Is the qubit in the ground state, no pi pulse. You see here's the qubit in the excited state with a pi pulse. And the maximum difference they recorded here was 61% for this particular device. So what's limiting it, and particularly what's interesting in quantum about what's limiting it? One is just the lifetime of the qubit itself. The other thing is that you're driving the system very hard. So there are a lot of photons around in the system. And so I think what's probably happening, and seems to have happened in most devices since, is that this is not so benign as maybe you would naively hope for it to be. So the fact that you're putting a lot of microwave resonators into this coupled system, they're probably inducing additional backaction and this sort of act of reading out. And so if the qubit then tends to relax, or maybe to get mixed between the ground and excited states while you're driving this system here, then you're going to get a lot of backaction, and that's going to reduce this fidelity here because the qubit doesn't stay still during this ramp-up process. Now afterwards, because the sort of latched readout is very robust against small changes, if it relaxes after that, and in this case it almost certainly did, I think they read out for several hundred nanoseconds here, and the lifetime was only 700 nanoseconds, it didn't matter. So it wasn't a Q&D measurement. The qubit was probably not going to be where you left it, but it was a high fidelity measurement, and for the time that was a big advance. Okay? All right, so that's exactly what he said here. The contrast is limited by relaxation during measurement. Now, that was the quantronium qubit. The thing that happened next was this sort of thing that we now call circuit QED, which is that they retrenched these charged qubits, had a really nasty behavior because of the charge noise of the substrates that they lived on, and there didn't seem to be any way to fix that. So as part of the retrenchment, they reinvented sort of the whole architecture, and now we have this thing called the Transmon qubit. So again, it's just taking a junction squid with a relatively small Josephson inductance, so that's a very small physical junction, shunting it with a modest capacitance, and now you get sort of a quantum pendulum who has a nice anharmonicity here. So again, this transition between 0 and 1 photons in the Transmon would be something like 5 gigahertz, and the difference in transition energy for each of the higher transitions is something like a few hundred megahertz. So it's not nearly as anharmonic as the charged qubit it replaced, but it's anharmonic enough. You can do a pulse on this thing in a few nanoseconds. And it's really, really insensitive to charge noise. So if I were to draw you the charging behavior of this circuit, it's basically flat bands. So now it doesn't matter if the background charge is messing around. So apparently he's chosen to call it a quantum pendulum here.
out of like some superconductors
You
or
make everything out of superconductors for low loss, but if you had some really good normal metal, it wouldn't matter, right? You know, if you had normal metal capacitors with a Q of 1 billion, we could use those. But we don't, you know, normal metal in nanoscale films that are 100 nanometers thick tend to have very high losses. So in practice, this whole thing is one big aluminum circuit. You can see it here. So this is a 3D one. In the 3D, I'll show you 2D and 3D qubits in a second. In the 3D ones, you can identify them because they just have these gigantic pads. The self-capacitance is kind of the nearness of these two guys times the length here. So that's just an edge capacitor of two parallel fingers of metal. And then the reason the pad is so big is to help give this thing a big enough dipole moment to couple to the resonator that we're going to bolt it in, as I'll show you. And then, of course, right in the middle. So that's the C. So again, this is the self-capacitance. There's some capacitance to the rest of the world that I'll show you on the next slide. That's determined by the height of this guy here. And then right in the middle, here's our tiny squid. Here's the area of the squid. And these two overlap junctions right here, that typically a few hundred nanometers by a few hundred nanometers, are forming this small junction and therefore this, large Josephson inductance. Small junction, large inductance. Parametric amplifier is a large junction, small inductance. Okay, questions here? Yeah. I don't have that particular graph in here. Okay, so names. It's called transmission line plasmon. Is that right, Ash? You were there when they named this thing. I think it's a dumb name, but they somehow decided that Transmon sounded cool, I think is the real reason. This is not an amplifier. This is just a qubit, right? This is replacing, we haven't gotten to the amplifier part yet. It is a specific, there are charge qubits. The one with a name is called the quantronium. There is there are flux qubits. They're called flux qubits. They don't have fancy names. There are phase qubits, which are kind of in between these two things. And then there's the transmon. The transmon is like a very flat phase qubit. These two are the sort of the most similar. But the transmon is basically, so phase, flux, charge, these are the quantum variables that encode the 0 and 1 state of the qubits. This thing is just an anharmonic oscillator. So that, I think the mon stands for plasmon. So it's really just an anharmonic oscillator whose bottom two states are separated enough that you can use it as a qubit. So that's why it doesn't have sort of a physical name. That's why it's not a charge or flux qubit. And it's in a sense, very boring, very, very boring, because it doesn't respond to any charge or flux or phase control knob very well. But that's why it's such a good qubit. It's because no matter what background offsets or local noise you have, it just doesn't care. So the reason it's the best is not because it's the most exotic, it's actually the simplest, and it's just the most stable. Okay? All right. So this, by the way, is probably 99% of every qubit alive today that's superconducting, at least by number. The second piece of the Transmon qubit is kind of the way we talk to it. So everyone takes their Transmon qubit. Here's my Transmon on the left. And we sort of take inspiration from real optical optics, and we hook it up to a microwave cavity or a microwave resonator. And we couple it capacitively to them, and then we couple the cavity to the outside world. So it's kind of an optics drawing of this thing. So here's my two-level atom in the middle. Here's the cavity. Light can live in the cavity and communicate with the transmon, and then light leaves to the right. So the transmon itself doesn't have any direct coupling to the outside world. Its coupling is mediated by the cavity. And this has several advantages. First, there's this thing called the Purcell effect, right? It's the fact that if you put an atom inside a cavity here on resonance, you can enhance the relaxation time of the cavity. We're going to use that Purcell effect backwards. We're going to put this transmon inside the cavity. We're going to tune the transmon frequency away from the cavity frequency, and then basically anytime the transmon tries to lose its photon to the outside world, it can't, because it's trying to make an excitation in an off-resonance cavity. So it helps these things live a long time. Here's the Hamiltonian of the system. We're going to pretend that the qubit only has 2 levels. So here's the spin state of the qubit, up or down. Here is the resonator of the qubit. And if you look at this second part, of the cavity, here's the resonant frequency of the cavity, and here's just the normal harmonic oscillator Hamiltonian. The neat thing is if you detune these two from each other far enough, you're into this sort of dispersive limit of the Jaynes-Cumming Hamiltonian. And now what you have, this is the key term right here, is you have a term chi sigma z times a dagger a. So what that says is, if you flip the state of the transmon, you change the frequency of the cavity and vice versa. So they influence each other, and that's what we're going to use for readout, but they don't exchange energy. So this is a dispersive interaction. So if you put a photon into your spin, if you flip the state of your spin, then your resonant frequency will go from omega r minus chi to omega r plus chi. And of course, it works backwards too. If you put a photon in your cavity, then your qubit will also move by that chi frequency. So they're coupled to each other. They influence each other's frequencies, but they don't exchange energy. And this is really nice for Q&D readout because we can now put energy into the resonator here, carry off information about the qubit, but not carry off the qubit's photon. And this is the key to circuit QED, and this is why the qubits are long-lived, why we can do rapid readout, and why that readout is Q&D. So this is sort of the most important change that went along with the transmon. And now, if you have one of these other qubits these days, pretty much everyone keeps the circuit QED architecture. You might graft a different style of qubit onto the left-hand side of the circuit, but this dispersive coupling sort of universally accepted to be the nice and the right way to hook up to these qubits. The key question of whether or not this is going to work is this G here. So basically, this is the strength of the coupling between these two. And the nice thing about these fake circuits is that real atoms are really small. Even, the people who nanofabricate cavities to go around those atoms have the same fab tools we do. Our atom is artificial. It can be made sort of arbitrarily large. Its mode volume can be tailored to match nicely whatever cavity you need. So even though you might think that this circuit might have trouble, in fact, we can make these couplings way stronger than we need. So in terms of cooperativity or these other terms you might have heard from optical frequencies, we don't have a problem here. It's easy to make this dispersive shift be plenty large, even for large detunings. And so a typical transmon and a typical resonator might have a G of a few hundred megahertz and a detuning of a few gigahertz, and then that will leave you with a few megahertz of dispersive shift. That's very easy to make a cavity with a similar lifetime, and then everything works out very nicely. Okay, and so again, you see here that the cavity frequency when the qubit's in the one state is shifted from the cavity frequency, and in this particular case, it's back. So here's what a
just one question in the previous thing. So you can do either ways, right? You can read the you can get a dagger a by reading sigma, and you can get sigma z by reading a dagger a. Right?
If you could talk to the qubit directly, you could figure out the cavity's frequency. We don't. So we only talk to the cavity, and from it we infer the state of the qubit. But for instance, if you want to shift the frequency of the qubit, you can apply an off-resonant drive to the cavity, and then use that to shift the qubit frequency around.
Okay.
It's like a Z gate.
Right. No, suppose my question is, suppose you want expectation value of sigma z.
Yeah.
That's easy to get because you can just see how much your frequency of a dagger has shifted.
I'll show you this in excruciating detail over the next 2 days. Basically, all we're going to do anytime we talk to a qubit from now on, you're right, energize this cavity, look at the phase of what comes out, or sometimes the amplitude, and that's going to encode the state of the qubit.
But I was thinking of what about the reverse? You can do the reverse also, right? Try to get the state of the qubit, and then from there infer what is the occupation number of the photons.
Yes, that's right. If you, because these shift each other, if you have a photon in your cavity and you try to drive the qubit, that's right. So you basically can do the spectroscopy backwards. You can put photons into the cavity, see what happens. Basically, you'll see a fanning out of the qubit frequency over the different Fock states in the cavity, and work backwards to that also.
So people do that also? Or? Okay.
It's a question of the ratio between chi and kappa. So if your chi is large compared to the kappa, then you can nicely resolve these different photon-shifted qubit peaks. If your chi is small compared to kappa, then you just get a smeary mess, and it's very hard to fit. So in my system, chi kappa is 1, it doesn't work so well. But in somebody, in a typical system at like maybe Rob Shulkoff's lab, they might have a chi kappa of 5, and if a lot of published data showing exactly what you're asking.
Even what about the statistics of the photons? Photon statistics?
Yeah, so you can look at the height and the area of the various peaks. And that's a standard technique for figuring out what the occupancy of your cavity is. So basically, if you have 1 part per 1,000 cavity and you photon occupancy in your cavity, then you'll get a main photon peak on 0 and a small photon peak on 1. And by comparing their areas, you can back out that's a way people back out the static occupancy. Yeah. Okay. So this is a 2D system. This is the whole circuit QED. So this thing is the qubit. There's the junction in the middle. These are the capacitor. They're more tightly spaced than the last picture I showed you. We call these things moose ears because it kind of looks like 2 moose antlers. This is forming the capacitor. And then this arm here and this arm here are capacitively coupling that transmon qubit to this now lumped resonator. So these fingers are the capacitance of the resonator. This meander here is the inductance of the resonator. This thing and that thing are in this case, differential ports that connect it to the external microwave drive. So this is a 2D system. This is a little old. These days, people have figured out that these closely coupled moose ear type capacitors put a lot of field in the surface where losses are. So if you see a 2D transmon these days, the capacitors are physically larger and physically spaced further apart. It's not changing the Hamiltonian, it's just changing basically the T1, the susceptibility to the losses in the circuit. Okay, and there, Vijay has nicely laid it out for us. And so the way this is made, depending on your laboratory, the substrate will either be silicon or sapphire. And this is typically made in 1 evaporation step. So we use a technique called Dolan bridges, where we basically have a suspended bridge to make the junction. Everything else, we just lay down aluminum from one angle, lay down aluminum from the other. So all these big features here are made out of sort of 2 layers of metal on top of each other, and only in this one tiny spot in the middle do the 2 layers kind of connect bottom to top through a Josephson junction. So it's very easy to fabricate sort of in 1 step on a bare substrate, and this is one of the reasons we keep the Q very high, is because we have very little sort of damaging and processing that has to happen to these circuits. Okay, here's the 3D one. I think maybe 3 or 4 years ago, these would have been the more common. I think 2D is coming back into style now as people figure out how to make the Qs higher. But here now, the transmon, as I showed you before, is kind of this 2 rectangular pads on this silicon chip here. And then this big hole is just a 3-dimensional microwave cavity. So it's lammed over 2 long section here. Something like, I don't know, 2 or 3 centimeters. It's probably a 7.5 gigahertz resonator. This particular one, you can tell that they wanted to have a squid in it because this thing is made out of copper. And this nasty looking thing is a superconducting magnet that's been wound and then coated in die-cast epoxy. So if you want to be able to penetrate flux into your cavity, you can't use aluminum. This does mean the cavity Q is somewhat lower, but it doesn't matter because we typically couple these to the outside world strongly enough that the losses here don't play a significant role. And once again, if we're going to measure in reflection here, the kind of response we're going to get due to this dispersive shift is that if the qubit's in the ground state, you get 1 resonant frequency. So the resonant frequency is right here. This width of this curve is set by the device Q, the readout resonator Q. If you excite the qubit, it shifts the resonator down. And now you see if you drive over here where the responses are the same, you get no information. So putting energy in the resonator does not measure the qubit. But if you sit right here in the middle where there's a large shift here, then the phase shift of the signal is going to encode the information about the qubit, so energizing the readout cavity will project the qubit. This goes back to your question. Okay. And then the other thing we have to do is manipulate the qubit. We typically have some other very weakly coupled port, and we just spray this port very strongly with microwave photons at the qubit frequency, and some tiny fraction of that signal kind of comes in. And as long as your generator doesn't end up dissipating so much energy in the fridge that it heats up, life is okay. So this Q would maybe be a few thousand to carry information out for the readout. This Q might be between a few million and a few tens of million. And if you make it too high, you'll just have a power starvation issue But that's, very classical, nothing to do with quantum mechanics. All we need to do is to make this port weakly enough coupled that 99.9 whatever percent of the information leaves this way and not that way. And that because you have these two ports, you could drive the system in transmission, and in that case you would get a phase or amplitude response. I think VJ in these cases is only driving it from this port and collecting the light from this port.
The transmission mode, is it not the earlier? I thought it.
So this cavity has two ports, a weakly coupled one and a strongly coupled one. So now you choose, depending on how you hook up the external, whether or not you're going to do reflection or transmission. If you saw a system with missing this here, you'd have only reflection as an option. So you have both options here. I'm pretty sure that the data we're all going to see today is reflection. But you might find in the literature someone else doing transmission. The architecture here of weak couple and strong couple, really it supports either way. It's just a sort of a philosophical choice that you make. Some people like transmission, some like reflection. There isn't here, right? So you don't know if this is being read out in reflection or transmission until I show you how it gets embedded in the external circuit, which I think is, hang on. Okay, it'll take a while till we get there, but I'll show you. Okay, and so now here we're just repeating this idea that we're going to drive this cavity with some amplitude and some phase, and we can express that in terms of the in-phase component and the quadrature phase component. So here's the IQ representation. And so even though there's a phase shift here, the discrimination between these two is best along, in this case, the Q quadrature. So it's nice to talk about it and think about a phase shift. What we actually do is in Q quadrature here, because that's the best way to discriminate. That gives the most SNR per photon rather than using the phase. If the phase shift is small enough, they're basically equivalent. If the phase shift is really large, really want to know what's the Q quadrature response here. And so the signal to noise of this whole thing is basically set by the signal, which is given by how big is the phase shift, which is determined by the Hamiltonian parameters and where I choose to drive. The drive amplitude, which is again just what I set my drive to. The noise is given by the 0-point fluctuations inside this cavity. And so we can get a very high readout fidelity in a few cavity lifetimes with a few photons. And the problem here for our room temperature readout electronics is that the typical power that we're talking about is something like, what is that? 1/10 of a femtowatt. This is a very, very small microwave power. So this is where, again, amplifiers come back into play as something to take this few photon signal from the cavity and boost it up to something that we can really record at room temperature. Okay, so now here is an example of, now we're still not back to the qubit yet. The qubit's going to live somewhere. Imagine that we've read out our qubit. We have the few photon signal. Now we're going to go back and ask how to build a parametric amplifier. And in this case, the circuit looks kind of identical. It's a junction and a capacitor. What's changed here to go from a qubit to a parametric amplifier is basically how much capacitance and how much inductance. So what we've done here is really increase the factor, the junction by a factor of 1,000 or so, and concomitantly made the inductance smaller. So we've increased the capacitance to keep the resonant frequency the same. And what that gives you is a very, very much weak anharmonicity compared to the Transmon. So the Transmon harmonicity is a few hundred megahertz. This guy may have an anharmonicity of a few kilohertz. And now we're going to go back to this duffing idea, the same duffing idea I presented in the beginning. And now it's going to be separate from the qubit, this separate object here. And we're going to go back and look at a different regime of behavior. So before, we would drive it with this strength here, where there was strong bifurcation, right? Over here, it's a linear oscillator that doesn't do us any good. But if we go just above the bifurcation point, then the system has a really high susceptibility, and it's going to be where we can generate our parametric gain. Okay. So this is now, again, back to pure duffing physics. You can tell VJ wanted to emphasize this because I don't even define what X is. Let's just imagine we have a nonlinear duffing type oscillator with a variable X. It's going to be phase of the junction in our case, but let's just keep it abstract here. You've got the sort of acceleration term, the damping term, you've got the spring, and now you pick nonlinearity here, and you're going to drive the system. So this is going to be a strong drive that turns the system into a regime where it's nonlinear. Again, the system is going to respond at the frequency you drive it at with some amplitude and some phase that have some complicated dynamics. And now to see that this system can be a parametric amplifier, the next step is to add a second tone. We're going to call this the signal tone. And it's going to be very weak, and it's going to be somewhere nearby in frequency, but not necessarily the exact same frequency. Okay, so then what I do is I say that the response of this variable x is going to be the same response I got with just the one drive, and I'm going to assume that the perturbation due to the signal is going to be some small perturbation on this big drive. Okay, so weak drive, this is going to be a small perturbation. And if you then work this way out, you get basically back the equation you started with, and you get now a new equation for just the perturbation in this y here. And what you see now is that here it looks like we're parametrically driving this system. Now it looks like the resonant frequency here is being parametrically pumped at twice the resonant frequency. So the question came yesterday, like, how is this fourth order thing a parametric amplifier? This is how. You drive it hard enough, you perturb it weakly enough, then in that frame it looks like a parametrically pumped amplifier. You'll notice that this is not the omega naught started with. You get this new complicated effective drive frequency, so it's a very crooked amplifier, but nonetheless it works. Okay, so remember, this is a Duffing type response that moves to lower frequency, so the plasma frequency is not what you get dynamically, and the pump strength, you'll notice here, is proportional to this thing times the effective kappa, and if I do this, yeah. You can kind of think of what I'm effectively doing is that I'm taking this cavity and I'm pumping its resonant frequency at 2 omega. And what that's going to do is to generate gain inside the device so that a small signal entering the cavity will now be a large reflective signal. And the strength of my coupling is basically how fast, how fast is given by the frequency, how much is given by the strength of my drive. Okay. And so now this comes...
Sorry.
Yeah.
Can I ask, what was the frequency of the photons inside the cavity?
You mean which set of photons, the signal or the drive? They're both
the
near,
drive.
they're both within a few line widths of the nonlinear resonant frequency.
Okay.
So they're going to be something like 1 or 2 or 3 line widths below it, depending on the gain. And the signal and the pump can be right on top of each other, and I'll show you that scenario in a moment, or they can be slightly detuned. And again, all these detunings are basically scaled by the Q of the system. Okay, so this now comes back to my work with VJ. We were trying to build a magnetometer. If there's time, I'll show you that later under applications. So we had this flux loop here that was testing our magnetometer. But in this particular scenario, we realized that the same system, if you now put this circulator on the outside, you can use this flux as just a static flux to move the frequency of your resonator. It's a very narrow band resonator, so it's very handy to be able to move it to match whatever cavity frequency you happen to have. And what we're going to do is to drive it very strongly, again at this detuned frequency, and then we're going to add some signal, and we're going to see parametric gain amplifying that signal, so it's going to be smaller coming in than it is coming out. And because of what I showed you yesterday, it's always also going to be associated with some idler signal, which in this particular case comes out at 2 omega d minus omega s. So if the signal is 5 megahertz above the pump, this one will just come out 5 megahertz below the pump, is how this works out. In this particular experiment, I guess the bandwidth is something like 10 megahertz. The added noise is going to be close to the quantum limit, and the frequency of the amplifier was like 4 to 8 gigahertz. So here, again, is this sort of Duffing response curve. So here's the pump frequency. In this particular scheme, we were fancier. We swept up and we swept down. So you can see the area of bifurcation. Here are the upper and lower response curves of this bifurcation, where they kind of come together. And then a little bit to the right is the region of parametric gain. So again, I'm approaching bifurcation, but not quite getting there. And if I want to understand sort of why this is a phase-sensitive amplifier, Vijay has this nice plot here to show you why this might be. So here's the phase response near the bifurcation point as a function of pump power. And so what you see here is that if I change the pump power, I get a strong change in phase. And so if you look here, if I have sort of a static pump here, and I add my signal as a small perturbation along the direction of the pump, you get a large phase shift one way. opposite direction of the pump, you get a large phase shift the other way. So you see that this thing is a strong transducer of changes of power along the pump to phase out of the amplifier. However, if you do the other thing, if you put your signal in quadrature with the pump, then you get a very small phase shift. And this is a nice intuitive way to understand why this Duffing type system is a phase sensitive amplifier. Because of the sort of the susceptibility of the system, it really likes it if you push it towards or away bifurcation. That gives you a large signal swing. If you just sort of move it, much at all. Okay, so now going back to the quantum Hamiltonian. So this is exactly what I showed you guys yesterday. Here's a harmonic oscillator. Here's the fourth order Kerr term here written in a funny way so that we can show you that what we're left with after the drive, when we get to the reduced system, is this sort of d dagger minus dd term. So this is exactly what I told you before. Now this lambda is going to be this parametrically controlled coupling of the mode to itself. And then the other thing you can do here, yesterday I told you to figure out that this is sometimes phase preserving or very similar to phase preserving amplifier, it is sort of split these dynamics is to define an upper and a lower branch. In his case, he calls it 1 and 2. Again, one's blue detuned, one's red detuned. And this will go back to just the exact same dynamics that I showed yesterday. So what that looks like in practice here is something like this. So here's your input signal. Here's the drive frequency, which the plasma frequency anymore. It's below it. And I'm going to put in my really loud drive, and I'm going to put in a very small signal. And so my signal to noise of this guy right here is just going to be some S to N, where this is the quantum fluctuations. Then what it's going to do is to generate an amplified output copy at that frequency and amplified idler copy at the other side. And what I'm going to do very carefully is notice that the noise here from the unused lower sideband will also get mixed in. So if I calculate now the new SNR, I have my amplified signal, I have the noise I started with, but I have this other added noise from the idler frequency. So I've degraded my SNR by a factor of 2. And this is, again, exactly this phase-preserving behavior. So one of the confusions about a phase-sensitive amplifier is that if you, asymmetrically, if you don't put your signal right on top of this center frequency of the amplifier, you get a phase-preserving amplifier, and anything you put in the upper half sideband will just be mirrored in the lower half sideband, and you're back to the same scenario and back to the same SNR degradation. The way to see that it's a phase-sensitive amplifier is instead to look at a single quadrature signal. And one thing you may have forgotten if you haven't looked at your microwave engineering in a while is that a single quadrature signal, let's say I do a phase modulation of a carrier or an amplitude modulation of a carrier, that's sideband signal. So it's always going to have 2 components here, up and down. And if I center that so that these guys are symmetrically detuned from the center frequency of the amplifier, now what's going to happen is that the SNR here, counting both copies, is 2S over N. And the amplifier is going to mix them back together. It's going to amplify this one and amplify that one and bring them together to these two. Now, these 2 copies are essentially identical to each other. I can record this one. I can record that one. I can, as long as I measure one, I can throw the other away because they've been amplified together. And now, because I have 2 copies of the signal and 2 copies of the noise, I retain my exact SNR that I started with. So this is the usual result that in a phase-sensitive amplifier, there is no SNR degradation. But to use it, you really have to tune your signal right symmetrically onto the center. And now, the other important thing to recognize here is that the phase of the pump is going to play an important role. I've shown the ideal case here, but remember, as I showed you before, there's a phase shift on these cross terms. If I set it the wrong way, I can destroy my signal to noise and degrade it strongly. Okay, so now back to the full setup. So here's my qubit, here's my cavity. VJ was using a differential drive, so this thing is a hybrid. You don't need to worry about it. It's just to convert a 2-ended signal into a 1-ended signal. He's now chosen to measure an reflection. You can tell because he put a circulator right here. So he's going to have a fused photon signal come in, interact with the cavity, fused photon signal go out. Now it's going to reach the parametric amplifier. It's going to be combined with the pump. And now you're going to get the output signal here that we want. So one important thing to notice here is there are a lot of circulators in this system because there are 2 problems. Number one, again, these operate in reflection. So you have an amplified copy of your signal headed right back to the cavity. But you also have this pump, which is very nearby. So you also have to worry about this pump propagating back. And so that's why there tend to be 2 or 3 circulators to protect against these 2 problems. Okay. So now they took this system, they hooked everything up, and they measured the first superconducting quantum with it. So what they're doing here is either exciting the qubit or not, and then just doing readout for a period of time. So here they're plotting the integrated signal as a function of time. So here's voltage, here's time, and what you can clearly see, these are individual time traces, is that you can see the qubits in the excited state in this particular trace, in the ground state in this other trace. It's not a particularly long-lived qubit in this example, so then the excited state tends to relax. And if the third trace, it relaxes at some different time. The key feature here is that if you read out for a few hundred nanoseconds, you can, with very high fidelity, tell what the state of the qubit is. And now in this case, because of this circuit qubit architecture, there is not going to be this extraneous backaction of having a really loud signal right strongly interacting with your qubit. So if you measure the qubit to be there, it's going to be there. It's really Q and D. Okay, so this was the first observation of these quantum jumps in the superconducting qubits. And if you average all the jumps together, you get back to measuring a T1 because the average decays at time. You see this particular qubit was nothing special, 300 nanoseconds. And so now the natural thing to do once you have quantum jumps now is to sort of mess things up. So in the quantum jump scenario, you just read out the qubit. All the changes in qubit state are the spontaneous jumps due to decay. What if I add some ongoing qubit Rabi drive? The qubit Rabi drive is trying to make the qubit oscillate between the ground and excited state. The measurement is trying to pin it to the poles, and then you see in what you get as a compromise between the two is this quantum xenodynamics, where if the drive is really strong compared to the measurement is very strong compared to the drive, and will only act by these sort of discrete quantum jumps back and forth between the north and the south pole. So you can see that very clearly here, and you get this random telegraph signal. So that's another sign that things are going right. The next thing we wanted to do was just to turn down the strength of the measurement. Basically, yeah.
Sure. So in this setup, you think the qubit is really the system you want to look at, right? That's the quantum system. And then can I think of like the cavity as the probe, and then you're doing projective measurements on the cavity?
Yeah, that's right. So right now, I'm going to allege to you that the amplifier is quantum, and the cavity probe is quantum. But I'm using all of that as sort of a sacrificial system, and I'm really only recording the information at the end. So you can kind of think of the cavity probe plus digitization as just the pointer variable for my standard projective measurement.
Pointer variable is the entire cavity qubit. The whole thing is the probe. Is the pointer variable? No, the final.
Right. The qubit is the quantum bit.
Is the quantum bit, right?
Cavity probe plus amplifying and digitizing together form the pointer variable that has the projective action.
But so what you talked about are weak measurements. That's right, right?
No, because these are strong measurements. Basically, these readout pulses contain enough information that they're really very strongly projective. So
But I thought your coupling between the qubit and the A is like it doesn't affect there's no energy transfer between.
Yeah, that's right. There's no energy transfer, but there is information. So basically, every photon that enters the cavity and comes out again carries a 90-degree phase shift, or whatever this is, maybe 50-degree phase shift, based on the state of the qubit. So if you ask yourself how many photons it takes to have a very strong certainty, to have a very projective measurement, it's a handful. So once a handful of photons worth of energy has transited the cavity, that's a projective measurement. And you can see that it's very projective because you see that here's the fluctuations, here's the separation. There's no way to be confused as to what the qubit state is. So this is strong measurements. What I'm going to do in weak measurements is to deliberately turn down the strength of the pointer variable until the quantum fluctuations are larger than the information content. So I'm not going to, these are coherent pulses. We like to describe them in terms of their average photon number, but the average photon number of a coherent pulse can be any small amount. I could send 1,000th of a photon through, 100th of a photon through. If I send 10 plus photons through, that's clearly a projective measurement. Even if I don't record that information, the universe gains enough information to destroy any phase coherence of the qubit. But if I just sort of tickle the cavity weakly with a very weak coherent state, it does not contain enough information for either me or any other observer to think that the qubit has been fully projected to the North Pole or the South Pole. And so what they're doing here in this next sequence of measurements is to do these what are called weak or partial measurements, where the information content of the pointer variable is not enough to project the qubit, and then to ask what happens. Because sort of we have this idea in our heads that measurement is projective, right? It's pounded into us in our quantum mechanical textbooks. And as an experimentalist, it's really easy to have a bad system with lots of noise. So it's very easy to say, an ideal version of the system, this would have been a projective measurement. It doesn't look projective to me because I've just added so much noise to the system that I've swamped my knowledge. What we're doing here is to take a quantum efficient system where neither you nor any other ideal observer have enough information to make a projective measurement out of it, and then to ask what happens to the qubit. Does that make sense? Yeah, maybe? Okay. So the idea here, again, in an ideal system, you mean these weak? You mean the weak? The weak measurement Yeah, that's you can do that, and we will do it here. But the idea is we're just trying to extract the fact that the weak measurement itself contains some information about the qubit evolution, and what information is that? We will use projective final measurements to prove our knowledge, but the overall idea here is that a weak measurement weakly perturbs the qubit state, but in a way that you know if your system is quantum efficient. So you don't need a final projective measurement to help you figure it out. Of course, in these experimental protocols where we're trying to prove it, we use that as a tool. But to sort of get ahead of myself, to give away the line a little, a weak measurement is one where the qubit moves a little, and it's again stochastic. You don't know which way it moves, but if you record the information in that measurement, you know where it is. So you go from an initially known state to a finally known state, but that known state is not the north or south pole. It can be basically anywhere. Okay, so again, in a quantum efficient system, here's some projective measurement. I'm going to turn this down in a quantum efficient measurement. So these amplified quantum fluctuations are going to be large compared to the separation of these pointer variables, and I'm going to just ask basically what happens. So if I start my qubit here along the x-axis, and I measure for a short period of time and I get a particular answer, I can basically do a Bayes theorem type update of my system and say, okay, what that means is that the qubit has moved a little bit towards the North Pole. If I keep measuring, the probabilities represented by this purple line are also changing, and let's say this time I get this guy, then he's moved a little bit more towards the North Pole, and if I allow the sequence to run on and on and on, basically what happens is the qubit will evolve. It can go up and down, it can go back and forth, but it will always be something that I know. So basically, a weak measurement is not a measurement that's projective, but I don't know the answer. It's just a small perturbation of the qubit that I can record and then know after the fact. I can't know where the qubit's going to go except for statistically, but on each individual measurement, my estimate of qubit state remains pure. Okay, so here's the experiment they did trying to prove this. And again, you're right that they, in this protocol, use projective measurements to basically prove that our calculations are working. So what they did is basically measure it once to project it into the ground state, put it onto the equator, do a weak measurement they digitize for some period of time, and then do a projective measurement on the end so that they can do tomography. And of course, this is kind of tomography in a random sense. You don't know which particular quantum trajectory you're going to get versus time. You just do a few billion, I don't know, a few tens of billion times. And what you can do is to basically take all of the trajectories that have the same integrated voltage, put them together with this tomography, and look at the x and the y and the z average state of the qubit from this tomography, and see basically that what it's going to do is that a weak measurement will kick you away from the y-axis, away from the x-axis and towards the z-axis. And if it kicks you enough, you go to the North Pole. And if it kicks you enough the other way, you go to the South Pole. But in between, you have this smoothly varying tangent-type behavior that will sort of kick you a little bit in between. So that's pretty strange. And notionally, if this is not perfect, but if the system was perfect, this x squared plus y squared plus z squared add to 1, I would know exactly where the qubit is, irrespective of which particular weak outcome I got. This is a phase-sensitive amplifier, though, and one of the big differences between today and tomorrow is this phase sensitivity. And one of the neat things you can do, so this is doing the right thing, if you like, amplifying the Q quadrature, the one that tells you the difference. So if you remember, is this an eraser? Yeah. My readout scenario was something like this. in a strong projective measurement, I have these two coherent states coming out of the cavity. They're large and well separated. What we're doing right now is to make them very small compared to the quantum fluctuations, but we're still using our parametric amplifier to read out the Q axis, which is the axis which tells me the difference between the ground and the excited state. But the other thing you can do is to use your amplifier to read out the I axis, which is the thing orthogonal to the thing that tells you about the ground and excited state. So you're basically measuring in an axis that makes no sense. And so the question is, what happens there? And the answer is basically you are gaining information orthogonal to the z-axis of the qubit. So what you're doing is gaining information that projects you, that perturbs you to the right or to the left on the Bloch sphere. So now you see you don't move towards the North Pole at all. The z value stays 0. What you're doing is kicking the qubit left or right around the Bloch sphere in a way that you know. So the larger the voltage, the more you've kicked to the left. The more negative the voltage, the larger you've kicked to the right. We call this like a stochastic Ramsey operation. It's a phase shift on the qubit. And you don't know which phase shift is applied until you record the value and write it down. If you didn't write it down, it would just destroy the phase of the qubit. But if you record this weak value, it is nicely measurable here, and you know the state of the qubit. So clearly these weak values are starting to be, weak measurements are starting to be a little strange, right? Because this one kind of makes sense. It kind of looks like a weak version of what you would get. With the exception of these X coherents, it's basically exactly what you'd get from just a strong measurement that you don't record very faithfully. This one has no classical analog. This is a purely quantum backaction on the phase of the qubit. So it turns out if you want to prove that your amplifier is quantum and that your pointer variable is quantum, measuring this guy and his properties, this stochastic Ramsey, is the best way to calibrate the quantum efficiency of your entire readout chain, of your parametric amplifier and your cavity and all the losses in between. And in fact, if you ask someone like Vijay and I how close you are to the quantum limit, we use these nice sort of paradoxical looking weak measurements because they have no way to sort of look classical and confuse us to calibrate our efficiency. I think the efficiency in this particular one was something like 50%, so halfway to perfect knowledge. So you'll notice if you look carefully that these things don't add and square exactly to 1, partly due to the T1 and T2 time of the qubit, but partly due to the inefficiency of the measurement. Okay, and if you want to do even more than that, you can do really trajectories. So now every one of these different colored curves here is us measuring for some time and looking at the voltage as a function of time. And the interesting thing here is that if you want to do this kind of check, you need to, at the end, do projective tomography. But if you get very picky about, for instance, I want just this one trajectory with all these very particular wiggles, you might have to do the experiment 1 trillion times before that occurs 1,000 times within some error bar to give you good tomography. So what they do is sort of, they take all the trajectories whose integrate to the same value here, and then they reconstruct the quantum state. And so, let's see, is there labeling? So one of these is the tomography that they construct, and the other one is this Bayes formalism estimation. And what you can basically see is good agreement. So you really can look at the individual evolution of the qubit, and with a quantum efficient amplifier, you can change the strength of the measurement however you want, but in all cases, what you see is what you get. Basically, if you know the qubit state before, you know how to interpret the readout, you now will always know the qubit state moving forward. So these measurements are really, they maintain the state, the purity of the quantum state. And so that should be a little disturbing, because it's kind of the opposite of this sort of projective measurement. We think that projective measurement is this thing that comes and squashes the coherence and pushes you towards the poles. Well, we see that really in this coherent state-based measurement, what's going on is your qubit is kind of undergoing a drunkard walk. And when it gets to the poles, it sticks. But it doesn't first die and then go to the poles. If your measurement is quantum efficient, it walks across the Bloch sphere and eventually gets stuck there. But you as the person sitting there and monitoring it would always see a qubit with a pure state. You will never see it sort of die and then resurrect. It will just kind of wander across the surface of the Earth until it gets to the poles. That's one of the really neat things about these weak measurements, and I'll show you a whole other set of arguments about this in a different way tomorrow. Okay, and so just to see this in action, this is a video, this is data. This is our tomography calculated evolution of the qubit as a function of time. And so in the red case, we basically put in our initial knowledge of the qubit, and we see it's doing the sort of drunkard's walk, right? You saw it first, it walked up, then it walked down. Eventually, the drunkard finds the south pole here. Oh, come on, it takes a while. Okay, and now at the end of this process, basically with enough time and enough tracking, we're back to something like a projective measurement. But the key thing here is that we didn't lose knowledge in between. We really can watch this guy walk all his way down.
Number of times, some of the trajectories will end up in the North Pole and some will end in, and the probabilities will be exactly what's the
yeah, I mean, it hit it better. But yeah, in this particular case, since your initial case is along the equator, 50% will walk to the North Pole, 50% will walk to the South Pole. If you just only pay attention to your final estimate, it'll look like a projective measurement. Of course, in experiment, T1 tends to favor the South Pole, so it's not quite 50-50, but it's very close. Now, the blue thing, oops, watch it again, watch the blue one. So the red one is we put it in the X state and we knew that. We put that into our estimator. The blue one is basically we said, well, what if we didn't know the initial state? We just didn't put in anything. So we start from the middle of the block sphere. And in that case, what you see happening is that basically, again, if it walks one way or the other, you see that like you kind of gain some Z information, but you never have any really quantum information. You never have any phase information about X or the Y state of the qubit. But eventually, and this is a different trajectory, when you do this, you will get to something like a projective measurement. And so the key thing to understand is our weak measurements are really like this red thing, not this blue thing. It's not that we lose the information and then gain it back slowly. It's that we always have it all the time. Okay. Right, and the key thing to remember here, to not get too excited, is that tracking is possible only if the initial state is known. If you really give me an unknown initial state, I will never see some spontaneous creation of these phases. Right, this is really only the case where you know the initial state, so it's a little bit of cheating. If someone gives you an unknown state, all you can do is the usual measurement, the usual tomography, where basically you can just get the final projective alpha squared and beta squared from an individual measurement. Okay, the final thing you can do here is to now go back to this idea of the Zeno effect, which is to say that I'm going to drive my qubit and not measure it. So here's my estimate of the qubit state versus time. There's no measurement back action, it's just doing a Rabi oscillation. If I'm doing a weak measurement, then what you see is that the measurement is sort of back acting on the qubit. So it's going to evolve away, right? The Zeno effect is going to say that the measurement perturbs the oscillations. And so eventually, as a function of time, the pure Rabi oscillation in red is going to get very out of phase with my particular trace in blue. And so what they did in this nice final experiment I'm going to talk about today is to basically feed back the measurement information into the Rabi drive to keep the Rabi drive and to keep the qubit always like a clock, always in phase. So what they're going to do is basically measure this difference between where they want to be and where they are, and slow down and speed up the Rabi drive so that they can keep this this measured Zeno trace going forever. So here's just them showing that they're doing a 3 megahertz Rabi drive. You see here that we're doing, if we look in the spectral information here, we get these peaks. If we measure harder, it gets broader. If we measure really hard, it becomes this sort of stair-step behavior when you really get quantum jumps. But they're going to stay in the regime where it's weak, and they're going to take this noisy trace, it actually looks way worse than this in real life, and the reference signal, which is saying the phase of the qubit that they want to maintain, and they're going to feed that back to as an error signal to the control of the system. So they're going to Rabi drive it, and they're going to measurement. They're going to take the information from the measurement, feed it back to the Rabi drive to say, oh, the measurement kicked it a little ahead, slow down, or oh, the measurement kicked it a little behind, speed up. And the neat thing they can do there is that usually you get this measurement-induced dephasing. You start Rabiing, you start measuring, you lose track of the phase, it's all done. But when you turn the feedback on, you can keep this thing alive. Not perfectly alive, right? You see that the contrast here is not 100%. But you can keep it alive for some arbitrary period of time here, milliseconds or something like where here is it died within a few microseconds. And you can even, for instance, let it die and then resurrect it with some particular timescale given by the error correction rate. So this is, again, just a way of showing you that the information encoded in these weak measurements tells you about the qubit evolution, and you can really use it to feed back and influence both your knowledge of the qubit and what its evolution is going forward. Okay, I'm running low on time, so I think I'll stop here and take any other questions you have.
Can the Zeno effect lead to a systematic shift of the frequency, or is it randomly either side? I mean,
Yeah, there's
go back a few slides.
A
sort of drag effect, or?
there's a AC Stark shift, which just always just like generically slows the qubit down. We're not so concerned with that, but the stuff we're tracking here is the dynamical shift. So in other words, just putting photons, just driving the qubit, changes the frequency a little bit.
I'm just wondering, if you're really trying to do a measurement of your frequency,
If you measure the frequency of the cavity while driving the qubit, it'll become a fuzzy variable, and that's kind of what's going on here. And as we're looking at,
but not systematically.
There's a systematic shift.
There is
the boring one, the AC Stark shift,
Mm-hmm.
and then there's the exciting one, which is the actual weak measurement, the actual the dynamical information comes.
So not a good way to do precision measurement, but.
Well, I mean, it's a way to make a clock, right? It's kind of a feedback system.
But you wouldn't want to shift your clock frequency by measuring.
Yeah, well, also the feedback scheme here relies on you having, where was that? Right, we're using some external clock to compare against also. So it's not really sort of an atomic clock type situation. And it's hard to get to an atomic clock type situation with microwaves because the stuff that we have commercially is really, really good. So we're not even looking for that kind of stuff. Right, the standard generator I buy has like 10 millihertz accuracy. Mm-hmm. So it's a pretty high bar.
Okay.
Yeah, this is more about not so much making a clock as proving that these weak, noisy measurements do have information in them, no matter how small or weak the perturbation of the system is. And I can always take that information, correctly apply it to keep knowing the system. Or in this particular case where there's a Rabi drive going on, even if I start from the unknown state, which is what I showed here, I can get back to a high state of knowledge of the system.
Amazing.
Any other questions? So I still had a question. So what exactly did you do to make it a weak measurement, like in the setup?
We just turned down the drive. So if you think about the average occupancy, if you think about the average photon number of a coherent state, we made that
the microwave drive.
Yeah, you just turn down the microwave drive until let's say the steady state occupancy of the cavity is much smaller than a photon.
Okay. And
I mean that's the strange thing, right? In the Fock basis, you think about you either put in a photon or you don't. Coherent states have an in bar, but that in bar is continuous variable all the way from 0 to infinity. So we can put in a pulse that contains on average 10 to the minus 5 of a photon. And so the net information coming out will be very, very small. So that's how we do that by just turning down the microwave generator.
Okay. And the other question I had was, so now you look at this stochastic trajectory of the qubit. Yeah. So this trajectory really is what I'm seeing is a system that's evolving under this. So there's some unitary dynamics. In addition, there's this weak measurement that's going on all the time.
That's right. There's a unitary Rabi drive, and then there's the stochastic perturbation of the actual measurement.
Okay, so the dynamics actually depends on this, like it's really shows is an effect of the perturbation.
That's right. If you can't do this on a trace by trace basis, and these are individual traces, I think, or maybe if you can't do it on a trace by trace basis, you can't get anywhere. This is not a thing that you can track in aggregate. On every individual run, you have to lock in to the qubit information. And if you can't do that, then repeating it multiple times and averaging this together won't happen. So those, and you can see very explicitly here that they often show the aggregate average data over many different experiments, but where is it? These are individual qubit trajectories that we're extracting information from. So these are individual instances. Mm-hmm. So in this case, there's no unitary part. The qubit's just holding still. There's only measurement backaction. The final experiment was to add some other Rabi unitary on top of this guy, some Rabi rate, to unitarily push the qubit around in the presence of this backaction, and then to look at them together.
Okay, so if there's no other question,
This is regarding a statement you made in one of your slides that tracking requires initial state. Tracking depends on the initial state.
Yeah.
But in two-state formalism, in weak measurement, pre and post state should be equivalent, right?
I'm not sure what you mean by that. Can you amplify that statement?
I mean, in two-state formalism of Aharonov, where it talks about this weak value measurement and weak measurement.
He's assuming there that you know the initial state.
No, but I mean, quantum mechanics is, I mean, time, the laws of nature do not depend on the initial state. Right?
That's right.
So in that sense, I was asking.
Yeah, that's right. So the qubit is doing what it's doing, but your estimate of it depends on your initial information. So if I have the same experiment and VJ has the same trace that I do, but I know the qubit started in plus X and he doesn't, our estimates of the final state will be different. Eventually, when the qubit has been projectively measured, they'll concur. We'll both agree that it goes up. But it's not that the qubit dynamics are changing, it's just your estimate of the dynamics. You know, your evolution of the stochastic master equation is influenced by your initial knowledge. So I hope that answers your question. It's just it's basically the filter doesn't change, just the initial conditions change based on what you know. Of course, in these experiments, I should know what I'm doing, but we sometimes turn off that knowledge just to make sure that the right thing is happening. You know, to make sure that throwing away that initial information does affect our estimate of the qubit's evolution. And in the weak values stuff, you do, I think, you assume an initial knowledge of the state followed by a strong projective measurement at the end. This is a different scenario where you say, I do the second half of the protocol, but somehow I didn't know what I started with, and that's the difference.
Okay, so I guess there's no other questions. Let's thank Michael again.